ideal gases versus real gases. The ideal gas law has always carried this little adjective at the front, ideal gas. An ideal gas is one that meets all the criteria of the kinetic molecular theory at all temperatures and pressures. It is always described by PV equals nRT. Of course, as luck would have it, you live in the real world, full of real gases. This is actually fortunate. The only reason that anything is a liquid or a solid, including you, is because the vaporized version of all of these things happen to be real gases, which allows them to condense back into liquids and freeze onward to solids. But our things that are gases at room temperature tend to show relatively ideal behavior at normal-ish conditions. And that's why we teach people the ideal gas law. It is an excellent, excellent description of behavior as long as you stay in what's kind of a reasonable range here. So in order to understand this, we have to go back to the kinetic molecular theory and look at when things might start to not be true. So let's get our little simulation back. Okay, so here's our simulation with our gases inside, and we can start looking at our kinetic molecular theory. So with our kinetic molecular theory, it says that gases are composed of molecules that are in continuous motion, traveling in straight lines and changing directions only when they collide with others or the walls of the container. Okay. That seems like something that would be true no matter what was going on. So I think we can put a check here. Always true. The gases aren't going to start to travel in a squiggly motion for no particular reason at all. Number two, the molecules composing the gas are negligibly small compared to the distances between them. Okay. So that's why every gas particle essentially takes up the same amount of space, because the particles are really little compared to the space between them. And so if the particles is really, really, really tiny, and there's like 100 times of space before you hit the next one, whether that particle is twice as big ends up being essentially irrelevant. However, if I put enough particles in here, very tiring, I can make it so that the blue space actually is a significant volume. I can also make the pressure ridiculously high here. So at some point, you simply have so many particles in there that they're packed so tightly together that if we were to consider the volume of this container, we would actually have to take into consideration that some of those spheres are taking up a significant amount of space relative to the entire container. As opposed to when things are normal, let's see if I can, reset. As opposed to a more normal set of conditions where you haven't got a ridiculously high pressure at all, the vast majority of a container full of gases is actually just empty space. So this one, the molecules composing the gas are negligibly small compared to the distances between them, fails at very high pressures. Because the particles begin to occupy a significant portion of the container volume. So essentially, it becomes so crowded that we can no longer pretend that the particles aren't taking up any space. Number 3, the pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. Check. Always going to stay true. Number 4, gases exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic and don't involve a loss of energy. Sometimes, gases, however, can turn into liquids. Imagine water vapor, for example, condenses onto your glass of lemonade. It got too cold, and the particles began to stick together. And every gas has kind of a threshold temperature below which the particles begin to stick together. And that's why we can have things like liquid nitrogen, dry ice, which is solid carbon dioxide. If you get the particles to moving slowly enough, they can actually stick together instead of bouncing off of one another. So at low temperatures, and what defines low depends on the gas. It's like temperatures close to their boiling point. And that's the boiling point of the individual gas, not like the boiling point of water. But at low temperatures, temperatures that are getting close to the boiling point, particles stick together. Or in other words, are attracted to one another. And as they stick together, if two particles stick together, now they only count for one in the particle count because they're traveling together, they're hitting the wall together, and so the net effect is you have fewer total particles because they're sticking together in little pairs throughout the container. The whole gig about average kinetic energy, always true. So if we get extreme conditions, very high pressures or very low temperatures, the ideal gas law begins to fail. But at just kind of standard room temperatures and things kind of close-ish to room temperature, the ideal gas law works very well, and we can ignore the identity of the gas. If you are ever to happen to need a very specific calculation on gases, there is a corrected version of the ideal gas law called the van der Waals equation. And I put it on the back of your sheet. It's not on your resource sheet because you're never ever going to have to use it in this class, but those of you going into engineering might need to eventually be familiar with the van der Waals equation. What the van der Waals equation does is it basically makes a correction for the other factors that are an issue. So in place of pressure in the ideal gas law, you use pressure plus n squared times A over V squared, which is basically accounting for the fact that the particles are beginning to attract to one another. And that little a is kind of a measure of how sticky the particles are, or what's their overall tendency to stick together. Essentially what this is that if the particles stick together due to intermolecular forces, they're traveling in pairs, and if they travel in pairs, the pressure is smaller than it's expected to be. So you have to add that little bit back onto the pressure to make this work again. The other issue is space taken up by the particles, and that's what this B value is right here. At high pressures, the particles are close enough to one another that the size of the particle becomes significant. This is essentially number of particles times the volume of an individual particle. And so the overall volume ends up needing to be corrected. If the particles are taking up space, it makes the actual volume that the gas needs to have be greater than what it's expected to be. So to make the calculation work, you have to subtract out the space taken up by the particles. Like I said, not something you're going to necessarily need for this class, but when you run across it later in life, I want you to just be aware that when they have to make very, very precise calculations about gases, they do have a way to correct for the type of gas, the amount of space it occupies, and how well it sticks together. For the purposes of this class, you need to know why the problems result. That as the pressure, or that as the temperature gets low, the pressure gets messed up because the particles are sticking together and not as many of them are available to hit the walls. And you need to know that as the pressure gets very high, that causes problems because the particles themselves start to take up some space. Okay, so that takes care of all of the things we need to take care of for that. At this point,